all of these recordings are popping up. I'm just processing the 10 hours of footage that we have. So they'll show up on the YouTube video, on the YouTube channel shortly. So we're now going to introduce the way that most organic chemists draw out their structures. And these are called bond line structures. So bonds are drawn in a quote unquote zigzag format with each line representing one bond. So for example, CH3 or ethane would be drawn as a line. So the key portions of bond line structure is that each start and end of a line, let me change colors for that. Each start and end of a line represents one carbon. So let me switch colors so that way we can see that. So as we notice, the two carbons in ethane are represented as the start and end of this line. Okay? All atoms have hydrogen atoms needed to have the correct formal charge and or a complete octet. And carbon typically has 4 bonds. So for example, if we're dissecting this bond line structure, if we wanted to fill this in and get a Lewis structure, we would need a total of 4 bonds to this central carbon. So as a result, we would need 3 hydrogens. How many hydrogens would we need for our right-hand carbon? 3, exactly. You want a total of 4 lines at the 4 lines connecting to each point. And what do these points symbolize? Carbons, exactly. Lone pairs are typically shown. Typically, there are some bond line structures where lone pairs are omitted. Can we figure out the number of lone pairs? Yep, we can use the octet rule. Okay, so to help you out, I provided a series of bonding preferences that details the number of bonds formed by each atom for a range of formal charges. We've already seen these bonding preferences before. Let's now talk a little bit on some rules for drawing out single and double bonds. So single bonds are drawn in a zigzag format. For example, if we're dealing with CH3, CH2, CH3, so first things first, I would draw one line to represent my first 2 carbons, right? Now, how many total carbons do I have? And how many do I have in this written formula? 3. So then, how many points do I need in my drawing? 3. So I'm going to draw a second line. And so in turn, each point on this line represents a single carbon. So we have 1, 2, 3 carbons. Now, as we've discussed previously, the number of hydrogens is implied for a complete octet. Let's just show the hydrogens for completeness on this bond line structure. So, first and foremost, on the far left carbon, how many hydrogens do we need? 3, exactly. 1, 2, 3. What about on the middle carbon? 2. 1, 2. Okay, and then finally, the right-hand carbon needs 3. Okay, so far so good. We're just fulfilling the octet rule. As you see, this bond line structure is far less work to draw, right? We've encapsulated all this information in just 2 pencil strokes. Now, let's now talk about our double bonds. Let's talk a little bit about the double bonds here. Double bonds are drawn with 2 lines. And just to show an example here, if we have CH3, CH3, CH2, let's look at this following structure just to appreciate an aspect of double bonds and sp2 hybridization. So first and foremost, we have how many total carbons in our structure? 1, 2, 3, 4. So how many points do we need to have? 4. Okay, so first things first, we've already we already know how to draw a chain of 3 carbons, right? So I'm going to draw one line for my first set of 2, and then to get my 3rd carbon, what do I need to draw connected to this line? Another line, right? Okay. So we've finished up the bottom portion of this molecule, right? We have 1, 2, 3 points for 3 carbons. Now, what do we need to have attached to our central carbon? What do we need to have attached to our central carbon? A double bond, like this. Perfect. Okay, now let's do some analysis here, and let's start to add in our hydrogens. Let's start to add in our hydrogens to this structure. So, first and foremost, for the left-hand carbon, how many hydrogens does it need? 3. Again, you're always looking for 4 total lines touching each carbon point. Does this middle carbon need any hydrogens? No, it already has 4 lines. The one on the right, I'm just going to spare us the effort. It's symmetrical, so it also has 3 hydrogens. What about this uppermost carbon? How many hydrogens does it have? 2. Exactly. Now, just a stylistic note, if we're dealing with an sp2 hybridization, what is the bond angle? 120 degrees. So does everyone notice how I drew my bond line angle with 120 degree separation between my bonds? It's really important. The last thing I want to see, and this is more common than I care to admit, is something like this, where you draw the double bond on the wrong bond angle side. Okay? Just make sure you're respecting the geometry of your molecules. Okay, likewise, just to note, triple bonds are drawn with 3 lines and are linear, 180 degrees. So for example, if we're dealing with CH3, carbon triple bond CH3, again, this is technically a valid condensed structure, although you can simplify this further. So starting off, what's the first thing that we need to do? If we want to represent these 2 carbons, what do we draw? Just one line. Because remember, each point on the line represents a carbon. Now, to draw this triple bond, how many lines do I need to draw? So 3 lines. 1, 2, 3. Okay, so we've established and we've accounted for these first 3 carbons. Now, how do I account for the 4th and final carbon in this structure? What do I need to draw? Just a straight line. And my question to everyone is, why am I drawing these lines straight instead of zigzag? Yes, it's SP. So if we think about this bond angle, it's 180 degrees. So it's not zigzag, it's linear. This is important. You really want to appreciate molecular shape, and your bond line structures are the best way to do that. Do we need to add hydrogens to this one, or are we pretty clear? Let's just do it, just for completeness sake. Okay, so let's switch to adding hydrogens now. So looking at the leftmost carbon, how many hydrogens do we need to add? 3. 1, 2, 3. Does this middle carbon with the triple bond need any hydrogens? No. Okay. So both of these middle triple bonded carbons do not need any hydrogens, and the one on the far right needs 3 hydrogens for a complete octet. Perfect. We're on our way to developing and drawing out structures efficiently. Let's now talk a little bit about some common mistakes. This is especially prevalent when we're dealing with formal charges. So if your carbon has a formal charge, you need to indicate the formal charge and add the appropriate numbers of lone pair to carbon. So for example, if we have CH3, CH2 minus, so if we have the ethane anion, keeping in mind that this methylene carbon now has a negative formal charge, let's try to write out a bond line structure. So first and foremost, we have 2 carbons. So how many lines do we need to draw? 1. Yep. Okay. Perfect. Okay. So we have our CH3, and currently we're depicting a second CH3. How do we show that this carbon has a lone pair and a negative formal charge? What do we write? Just write the lone pair. Exactly. And we then have to specify the negative formal charge. Okay. Perfect. Not too bad, right? Yes.
So the negative formal charge would be
It would be on the carbon with the lone pair. Yep. And let's now show that by adding in our hydrogens. So let's draw out our basic skeleton. Considering that we have a lone pair, let's now consider how many hydrogens we need for a complete octet. So for our leftmost carbon, how many hydrogens do we need? For our leftmost carbon, how many do we need? 3. Exactly. We want a total of 4 bonds and or lone pairs to carbon. Okay, looking at this rightmost carbon, how many hydrogens does it need to have a total of 4 bonds and or lone pairs? 2. Yep. And of course, never forget to keep including your negative formal charge. That specifies that we have a negative charge on that carbon in particular. Does that make sense? Okay. Just for an example, if we were looking at CH3, CH2 plus, how would we write out a cationic species? So we have 2 carbons, so what do we need to draw? How many lines? Just 1. Yep, 1 line just as before. Now, my question to all of you is, what's one thing that we have to do differently? What do we have to specify for one of our carbons? Positive charge, that's it. There we go. Do we need to put any lone pairs in this case? No, because it has a positive formal charge. It has less bonds than usual. Okay, rule number 2, we've already discussed previously when we talked about the sp2 hybridization and the trigonal planar geometry. Essentially, if you're drawing out any sp2 hybridized carbon, you want to make sure your bonds are separated by 120 degrees. So this is acetone, CH3, CO, CH3. It's a common solvent that you'll be using. Please do not draw out your double bonds like this. This is not respecting the bond angles appropriately and is incorrect in bond line structure notation. Does that make sense? Okay. The other thing that I want to mention is that if we're dealing with heteroatoms, must be drawn with the appropriate number of lone pairs, and you in general are required to draw the hydrogen atoms attached to heteroatoms. The lone pairs for some bond line structures are not included, but I would prefer, if I ask you to draw a bond line structure, that you include the lone pairs. So let's see how this works in action. Let's look at CH3OCH3, or dimethyl ether. So first and foremost, if I need to represent a carbon, what do I need to draw? A line, yep. Okay, and what is the carbon, the methyl carbon bonded to? What is it attached to? Oxygen. So we're going to draw the line attached to an oxygen. Does that make sense to everyone? Now, what is attached to this oxygen? Another carbon, so we draw a line out. Perfect. Now, how many lone pairs does this oxygen need? 2. Exactly. So let's draw that out. One, 2. There we go. Perfect. Does that make sense to everyone? The reason why we draw the lone pairs on our heteroatoms is to help reflect and identify sites of potential reactivity. Okay, and then finally, If an atom is sp hybridized, you want to make sure your bond angles are 180 degrees. In cases where you're dealing with an alene, an ambiguous carbon can be represented by a dot. So what do I mean by that? What do I mean by that? So if we're dealing with CH2, CO, this is the structure for a ketene derivative. Let's think a little bit about how to process the following structure using bond line notation. So what's the first thing I need to draw? I have two carbons connected to each other, so what do I need to draw first? A line, yep. And I'm going to draw this line in a linear fashion, and you'll see why in a moment. Okay? Taking a look at these two carbons, what do you notice is a little bit odd about these two carbons? One has an oxygen, but do we notice a lot of hydrogens? No. So then, taking a look at this structure, we're going to draw these two carbon atoms connected to each other, right? Now, I'm going to show you the Lewis structure to help everyone see what we're doing when transcribing this structure into a bond line notation. So we've drawn the following Lewis structure on our previous quiz. Now, our goal is to transcribe this Lewis structure into bond line notation. So we have our first, oh, whoops, one more carbon. Let me reflect that. CH2CCO. Perfect. Okay, so we have our first carbon-carbon bond. And since there's a double bond, how many lines do we need to draw between our carbons? 2. Essentially what we're doing is we're taking this bottom structure, we're omitting the carbon symbols, omitting the bonds to hydrogen, and in turn, we have generated a bond line structure. So we've checked off these first two carbons. Okay, now what is attached to our central carbon? Another carbon, and what type of bond is linking these two carbons? Double. So let's draw a double bond. Now, it's really hard to tell if you just have two double bonds adjacent to one another if there's a carbon in the middle, right? It's hard to tell if it's a typo. So in order to adequately showcase this carbon, you represent an alene carbon. This is known as an alene system with a dot. That way it's unambiguous. There is a carbon in the middle. Does that make sense to everyone? Okay. Finally, attached to this carbon is a double bond to oxygen. And we put another dot because it's an alene type system, where it's ambiguous whether a carbon is present in between that set of double bonds. Does that make sense to everyone? Yes.
How do you do the, you say we have to do the respect the angles, right?
Yes.
How do you respect that?
Yes. So thinking about the hybridization of these two carbons, what are the hybridizations of those two carbons? sp2 or sp? Sp, exactly. So then both of these bond angles are 180 degrees. Does that make sense? Perfect. Finally, as our last finishing touch, we put the lone pairs on our oxygen. There we go. So ketene looks quite odd in bond line notation, and this ketene variant certainly reflects the odd behavior and odd structural characteristics of these compounds. Any questions on bond line notations and alene carbons in particular? Okay, let's keep moving on then. So I'll start us off, and we're given a Lewis structure. Let's now convert this Lewis structure into a bond line structure. So what I'm doing is I am omitting all my carbon-hydrogen bonds, and any carbon is just represented as a point on a line. So first and foremost, let's switch pen colors for this. I'm going to, this OH, do I need to include heteroatom hydrogen bonds? Yes, so I'm going to draw this OH. It can also be condensed as OH, depending on the text that you see. But for now, I'm going to draw my OH longhand, and I'm going to put my 2 lone pairs for a complete octet. Next, I have a set of 2 carbons, so I'm going to draw a line. These 2 points on the line represent my 2 carbons. Does that make sense? Next, I'm going to draw this carbon connected to an oxygen atom, and I'm going to draw the 2 lone pairs on my oxygen atom. What is attached to that oxygen? Reading from left to right. No, yep, another carbon, so I draw a line. Next, I have a carbon-carbon triple bond, so I draw a line, and then connected to that point, I draw a triple bond between my 2 carbons. Okay, perfect. So now we're right here. Next, I have a carbon-carbon double bond. So then, to this carbon, I need to draw how many lines attached? 2, exactly. Okay, and then off of this carbon are 1 CH3 group and a second CH3 group. And to represent these CH3 groups, how do I draw them? Just a line, exactly. 1, 2. There we go. So we have a complete bond line structure for this molecule. Does that make sense to everyone? Yes.
So you include the hydrogen bonded to the oxygen because
It's a heteroatom. Anything that's a non-carbon atom. It can also be abbreviated like so to represent that it's a hydroxyl functional group. But for now, I'd like to explicitly draw out the heteroatom hydrogen bond. So to help everyone practice on this, what I would like everyone to do now is to write out a valid bond line structure for the following molecule shown. Remember, you are to write out all heteroatom hydrogen bonds. Yes. Yeah. Yes, and then attached to 7 are 2 methyls. Yep. Yep. So then instead of having another methyl attached to 8, I would just erase these 2 appendages, and attached to 7 is another line. So attached to 7, so there's another carbon. Yeah, so that's why we draw. Yep, exactly. Yep, exactly right. Yep. Yep, looks good. Okay. Yep, looks good. Yes. Because there's a lone pair that would result in a negative formal charge. One dot indicates a dot, which has a different formal charge actually. So let's now take this structure and let's write out the bond line structure. So first and foremost, we read off. So we draw out all of our heteroatom hydrogen bonds and we put our lone pair. Now, to respect the fact that this nitrogen is indeed trigonal pyramidal hybridized, I'm going to next connect it to a carbon at this bond angle. Mainly because the reason why we draw our carbons in this zigzag pattern has to do with the fact that carbons have a tetrahedral geometry in most cases, right? So it would not make sense for me to draw my bond angle going down. At least this way I'm preserving the fact this nitrogen is trigonal pyramidal. Does that make sense? Okay, we draw our carbon-oxygen double bond. Then connected to that is a carbon that is double bonded with another carbon. We then draw our oxygen connected to this carbon. And we draw our oxygen-hydrogen bond. Finally, we draw out our CH3 group just as a single line. Perfect. Just some side notes on this. I'm going to adjust this double bond to more reflect its geometry. So when I took a look at my structure, it didn't quite reflect the 120-degree bond angles of my double bond. So I redrew it to more accurately portray the double bond geometry. Does that make sense to everyone? Additionally, notice how this double bond has some stereochemical information. So I need to make sure my hydrogen and my methyl group are on the same side. So let's redraw this to reflect that. So my hydrogen and methyl group are on the same side of the double bond. And then finally, we draw out our amide functionality. So now we have a complete bond line structure that respects the geometry of our double bond. Notice how these two substituents are on the same side of the double bond, and it reflects the bond angles for each of our hybridized atoms. Does that make sense? Does that pattern of revision make sense? Yes.
So what is the hydrogen included in there, even though it's not well, it's attached to a carbon?
It can be omitted in this case. I was showcasing it just to help everyone see that we need to draw the amide opposite to the methyl. Yeah. Does that make sense? So just always pay attention to your double bond geometry. Cis and trans are entirely different compounds, as we discussed last class session. So you want to make sure you're transcribing the correct isomer. Does that make sense to everyone? Okay. Let's now keep going and let's try a few more practice examples. This time we're dealing with anionic species. I'll start us off and then I'm going to have you do too. Okay? So, looking here, we have a carbon anion right here. So I'm going to draw my first line to represent these first two carbons. Next, I'm going to draw a lone pair and a negative formal charge on this carbon because it's a carbon anion. Does that make sense so far? Next, I'm going to draw a connecting line to represent this next carbon. Attached to this carbon is a double bond and an OH motif, or a hydroxyl motif. Notice, and one thing I do want us all to pay attention to, what is on the same side of our double bond? What do I need to draw on the same side of this double bond? What do we call that motif? The carboxyl, or carboxylic acid. Let me make some space for it. Okay, perfect. So we've respected our double bond geometry. I'm going to draw out my lone pairs on the ketone functionality in our carboxyl group. And then finally, off of this double bond, I have a carbon-carbon triple bond. How do I need to draw a carbon-carbon triple bond? Linear or bent? Linear. So exactly like a dart. There we go. Remember always to draw your linear carbons as straight linear structures. Does that make sense? Okay. Any questions on this example? Well, let's see how we do. I'm going to have you now attempt drawing bond line structures for the following molecules. These are common intermediates that you'll see throughout this class. Everything going okay? Yep, that's good so far. Everything going okay? Yep, that's good. Yep, that's good. Any questions? So just like before, every point on the line represents a carbon. Everything going okay? Everything going okay? Yep. Which one? For the CH3? What does it look like a little bit? Like the carbons? This, yeah. So but I would draw it like in the same geometry, like a triangle, because the carbons are arranged in a triangular shape. That's known as a cyclopropane. Think that probably if you got rid of the carbon and just draw the arrangement of bonds, it's almost shaped like a triangle, right? Yep. That's called a cyclopropane. Yep. Yep, looks good. May I check? Everything going okay? Yep, looks good. Everything going okay? Yep, looks good. Just make sure this is 5, not 6. Oh, yep. Yep, looks good. So I saw a lot of reasonable solutions to the first portion of this problem. So let me talk a little bit about this. So in drawing bond line structures, each point represents a carbon. So I'm going to start off up top here. So I'm going to draw out my carbon-oxygen double bond, and I'm going to put my lone pairs. Perfect. So we've established the first part of this molecule. Attached on the right-hand side, does this carbon have a lone pair and a negative formal charge? Yes. So I'm going to put an appropriate lone pair and a negative formal charge. Attached to this carbon is a carbon-oxygen double bond and an oxygen-hydrogen motif. Perfect. So we've drawn out carboxylic acids in previous examples. This bonding motif looks exactly the same in all bond line structures. Okay, next we have a cyclopentyl or cyclopentane ring for 5 carbon ring. What does it look like to everyone? What kind of geometric shape? Yeah, like a pentagram. So each point on the pentagram represents a carbon. Okay, now on the right-hand side, we have an interesting cyclic motif. How many carbons do we count in this ring? 3, yep. And what does it look like to everyone? A triangle. This is known as a cyclopropyl group for 3 carbons. Perfect. So we've drawn out the following bond line structure. Each point represents a carbon. As a bonus example, let's look at the next structure. So starting off, we have a CH3 group connected to a carbon with a lone pair. So I'm going to start us all off by drawing out my CH3 group and a carbon with a lone pair. I always like to orient my molecule in a way where I'm writing it from left to right. Makes it easier on me, makes it easier to read, overall nicer note-taking. Now, attached to the carbon with the lone pair, we have what? What's attached? Yep, just another carbon, yep. Now, attached to this next carbon, we have what 2 functionalities? What's the first group attached? What's the first thing? Yep, first we have a carbon, so we need to draw a line. And then what else? What's below? Yep, a protonated amine, otherwise known as, it's an ammonium derivative. Okay, so we draw our nitrogen. Yep, we draw out our 2 nitrogen-hydrogen bonds. We draw out our positive charge. And then we just have to respect the fact that this nitrogen is tetrahedral. So you want to make sure your bond angles reflect that tetrahedral geometry. And then finally, attached to the nitrogen is what? Yep, just a methyl group, a CH3. Perfect. So we've completed drawing out bond line structures for these charged species. Any other questions on this? If not, we're ready to continue on now. So let's now take some practice drawing a line structure from condensed structures. So your book will present you with a series of condensed structures, and our goal will be to quickly draw bond line structures. So given we have CH3, CH2, O, CH2, CO2H. The fastest way to draw bond line structures is to recognize functional groups. So let's start us off and let's switch pen colors for this. This first, oops, I didn't switch pen colors. One moment. Let's go with the other method to do this. Okay, so looking at this first arrangement of atoms, what do we call that functionality? Carbon, oxygen, carbon. What do we call it? Ether, exactly. So this is an ether functionality. Okay, what do we call this CO2H? What is that shorthand for? What is that the condensed formula for? Yep, carboxylic acid. Carboxylic acid. And the reason why I want you to recognize functional groups is it allows you to quickly draw bond line structures. So for example, my first two carbons I represent with a single line. Ethers will always look like this. We draw our line connected to our oxygen and then our line connected to our second carbon. So this ether functionality, if you can recognize it, you can quickly draw it out. Finally, what's attached to this next methylene carbon? What's attached? Carboxylic acid. And a carboxylic acid always looks like this. So by recognizing your functional groups, you can quickly draw out a bond line structure for your molecule. Let me zoom up a little bit so that way we can see. There we go. Does that make sense to everyone? Yes.
I thought that if O was what we wanted to see, then it would be like busy
in this case, I've retained the 120-degree bond angle. The reason why I would be facing up would be if this this bond angle was turned up. So what you're meaning is something like this, right? Well, if we rotate this 180 degrees, we get the following. So all I've done is rotated our bonding arrangement 180 degrees to accommodate the fact that if I look at my zigzag pattern, this carbon will be on the bottom portion of the zigzag. So just to showcase the bond angles. As we can see, this bond angle is roughly 120 degrees. You never want to have your double bond pointing directly in between your carbon-carbon bond angle, because that would imply a bond angle that's not a 120. Does that make sense? Perfect. Okay, what I want you now to do is to take a moment, look at the following condensed structure, and try writing out a bond line structure. And for those in the back, let me write this out fully. So we have CH3, 2, CH, CH2, OH. And then I'm just going to change pen colors really quickly. There we go. And I'll walk around and check to see how everyone's doing. Everything going okay? Everything going okay? Yeah. Yeah. Yeah, that's good so far. Any questions?
The CH, so how do you show it?
It's implied by the number of carbons connected. Yep. Just make sure I account for the fact that these CH3s are probably both connected to that carbon.
Oh.
Yeah.
Okay.
Does that make sense? Yeah. Perfect. Any questions? Yep, you're correct. It's an alcohol. Yep. So I saw a lot of reasonable responses. Let's now talk about this problem. So if you're ever feeling stuck drawing a bond line structure, you can quickly write out a Lewis structure and then just transcribe it over. There's nothing wrong with that. I won't be able to tell. It's not like you'll lose points for it. Now, let's do a little bit of functional group recognition here. The OH, COH, what do we call that? Alcohol. Perfect. And by recognizing our functional groups, we can draw them out. So if we're converting this Lewis structure into bond line, I have a carbon that's connected to two methyl groups. So I'm going to draw my first line to represent my first two carbons. Now attached to this carbon here, I need to draw what coming off of it? If it's attached to a methyl group, I need to draw what? Yep, draw another line, right? Okay, perfect. Let me draw this straight down since it's tetrahedral. Okay, now what else is attached to this carbon? Another carbon, yep. And then what's attached to our CH2? What's attached to our CH2? An oxygen, or more specifically, an alcohol. So we can write this alcohol as an oxygen bonded to a hydrogen. And an alcohol will always look the same. It's the same arrangement of atoms and same connectivity of atoms. That's what makes it a functional group. Does that make sense to everyone? So let's just check our work here. We have 1, 2, 3, 4 carbons. I have 1, 2, 3, 4 points. So I didn't make a mistake. Any other questions on these examples? Yes.
How would you recommend you draw the leftmost carbon so it doesn't appear to be trigonal? Like, is there a little
we typically draw them using a zigzag pattern. There's nothing wrong with it appearing like it's trigonal planar currently, because it's just convention to draw the carbon connectivities in a zigzag pattern. If, for example, there were multiple carbons bonded to this atom, you draw it in a bit like a cross pattern, like this, where it's making almost an X. Even though it's not entirely reflective of the true tetrahedral bond angles, the reason why we draw it this way is so we can readily use what's known as dash wedge notation. And this perspective of looking at these molecules, it's like we turned our molecule on its side. So we're looking at it from a side-on perspective. That's why the zigzag chain is apparent. And we'll see that when we play with some models in chapters 3 and 4. Okay, let's keep moving on here. So let's now take a moment and let's just appreciate the fact that we can draw Lewis structures from bond line structures. And our rule is the start and end of a line each represents a carbon atom or a non-carbon heteroatom if the symbol is shown. Now, carbon typically forms 4 bonds, so we can add hydrogen atoms to each atom to reach a complete octet. Just please make sure you're checking your formal charges. So let's do an example, and I'll start us off. If we wanted to draw a Lewis structure from the following bond line structure, my first order of business is to take each point and write it out as what? What does each point represent? Carbon. Okay. Okay, next thing I'm going to do is to each carbon, I'm going to add hydrogens to reach the desired formal charge or complete its octet. In this case, we're completing its octet because the formal charges are all 0. So to this first carbon, I'm going to add 3 hydrogens. Let's switch pen colors for this. What about to this second carbon here? It currently has 3 bonds. How many hydrogens do I need to add? 1. Exactly. What about to this next carbon here? 2. 1, 2. Okay, let's take a look at this double bonded carbon. Yep, exactly. And then finally, would someone else from the class be able to contribute how many hydrogens do I need attached to each of these methyl groups? 3. Perfect. Perfect. So we've expanded out this structure into a Lewis structure, and boy, does it look like a mess, right? Let's now take a look at the following bond line structure, and I'd like you to convert the following bond line structure into a Lewis structure, just to practice, because I want you to be able to count hydrogens on a carbon, because that gives you insight on the reactivity of that carbon and the steric environment of that carbon. Everything going okay? Everything going okay? Yep, that is transcribed correctly. And all you have to do is replace each of the points in the line with a correct. Everything going okay? Yep, that's good. Everything going okay? Good. Just, oh yes. Yep, we got carbon correct. Good. Yep, that's good. So everyone's moving pretty quickly through that. That's okay. And if you're slightly behind, don't worry. Practice makes perfect. You'll get much faster at this the more you go through the book and the more examples we do. So let's take a moment and let's replace every single point with a carbon. So we have my oxygen, hydrogen, my OH functionality, my alcohol. Attached to my alcohol is a carbon. Attach that carbon, oh, that's messy, is a carbon-carbon triple bond. And then attached to this carbon is a carbon-carbon double bond. And then finally, attached to this carbon, and let me scoot over just a little bit so that way we can see it clearly, are 2 other methyl groups. Now that we have our carbon skeleton drawn, I'm going to switch pen colors and we're just going to fill in our hydrogens. We're going to fill in our hydrogens. So from left to right, this first carbon bonded to the alcohol, how many hydrogens do I need? 2. Okay, do these triple bonded carbons need any hydrogens? No. What about to the double bonded carbon right here? Just 1. Again, you're aiming for a total of 4 bonds. Does this double bonded carbon need any hydrogens? Does it have 4 bonds already? Yeah. Okay, and then finally, each of these methyl carbons need how many? 3. Yeah. Perfect. So we've expanded out this bond line into a Lewis structure. As you see, which structure do you prefer to look at? Bond line. It's by far more convenient. That's why we've developed it. Okay. So, any other questions on this? Okay, let's keep moving then. So, there's one trick. If you know the bonding preferences for your atoms, you can list the number of hydrogen atoms bonded. based on the formal charge. So to showcase how this works and how to fill in both hydrogen atoms and lone pairs, let's take a look at the following example. So this is quite an interesting species. It's a nitroethane derivative. Anyway, so or a beta nitroester if you're going to be specific. Anyway, let's start first and foremost by replacing each point with a carbon. So we have how many total carbons in this structure? How many total points do we have? 4, because there's one more. Don't worry about that. Okay, so we're going to write out our carbons. And we're going to connect them to each other. Now, we're going to need to be a little bit attentive here on our formal charges. Does this carbon have a negative formal charge associated with it? Do we see a negative charge drawn? Yes. So in some cases, you'll only be given the formal charges associated with a given atom. And this is really important now. Because this carbon has a negative formal charge, what do I need to draw on that carbon? A lone pair. Exactly. 3 bonds and 1 lone pair gives us a negative formal charge on carbon. That's a textbook bonding motif. Finally, let's expand out our ester. Now, for Lewis structures, you're welcome to abbreviate your methyl side chains in many Lewis structures. So if it's a common side chain that you can write a condensed formula for, you're welcome to do so, if that's more convenient. So for example, we can write this out as CH3. If you're drawing a mechanism where you need to show the carbon-hydrogen bonds, then you should write out all of the carbon-hydrogen bonds. Now, to fill in some lone pairs here, this nitrogen has a positive formal charge and 4 bonds. Does that check out? Yeah. Okay. This oxygen in this nitro group, this functionality here is called a nitro group. Because the oxygen has a negative formal charge, it has 1 bond and how many lone pairs? Taking a look. 3. Yep. This is why I like bonding preferences, because it saves you from a lot of hassle if you're trying to figure out how many lone pairs and how many hydrogens I need to draw. Does that make sense to everyone, how this works? Okay. To make sure we're on the same page here, what I'm going to have you do next, oh, I forgot the lone pairs on oxygen. Really quickly, 0 formal charges. We have 2 bonds. How many lone pairs do I need to draw? 2. 1, 2. Perfect. Okay, now I'm going to let you loose on another example. This time we have this is an amino acid. For those biologists who are so inclined, you may be able to tell me the name of this amino acid. So we have a carboxylate and a protonated amine and a urea functionality. So have at it, converting this structure, accounting for the formal charges, into a Lewis structure. Everything going okay? Any questions?
No, just
No. Any questions? Okay. Any questions? Okay. Any questions? Okay. Yep. Try filling in the lone pairs on the negatively charged oxygen. Everything going okay?
so decided.
Yep. It's good so far. Everything going okay? Yep. It's good. Yep. Looks good. Yep. Looks good. Okay, let's now talk about this. Anyone want to tell me a name? We'll have to look it up since I forgot entirely, but would any of the biologists in the room, they have you memorize the amino acids, right? Not yet, at least. Okay, I'll give you a name next class session for those inclined. For now, let's look at each point. And each point is converted into what? Carbon. Yep, so let's write out all of our carbons. And I'm drawing out all my heteroatoms as well, just to make things a little bit easier on us as we move forward. This functionality is known as a urea functionality. This is a carboxylic acid. And this NH3 functionality is an amine, but more specifically, it's a protonated amine that we call an ammonium. Okay, so we have our rough skeleton in place. Now all we have to do is fill in our hydrogens and our lone pairs. So then, keeping in mind that we have a nitrogen with a positive formal charge, how many hydrogens are attached to that nitrogen with a positive formal charge? 3, yep. A nitrogen with a positive formal charge has 4 bonds and 0 lone pairs. This is why, if you're fast with formal charges, this part is not too bad. Now, this oxygen with a negative formal charge has 1 bond and how many lone pairs? 3. 1, 2, 3. Perfect. This ketone oxygen, well, the carbonyl oxygen in the carboxylic acid has how many lone pairs? 2 bonds, 2 lone pairs. Yep. Okay. What about this carbon here? How the carbon attached to the amine functionality? How many hydrogens does it need? 1. Okay. What about all 3 of these methylene carbons? How many hydrogens do they need? 2. So just in case you're curious, a CH2 is a methylene functionality. It's just our common way of talking about this very common unit. Okay, looking at this nitrogen with 2 bonds and 1 hydrogen, how many lone pairs do I need to put on that nitrogen? 1. Again, we're aiming for a complete octet. Okay, what about this urea carbon? Does it need any hydrogens? No. Thankfully, I gave you the hydrogens attached to each of these nitrogens, and we can put our formal charges. Do any of these 2 nitrogens need an additional lone pair? Which one? The one on the bottom or the one on the right? The right. It needs how many lone pairs? 1. Perfect. The reason why I want to be able to visualize lone pairs is they're often the site of reactivity, typically basicity, as we'll see in the next chapter. Any questions on these examples? Okay, let's keep going then. We're making good progress today.
Good question. Does that atom has a negative charge?
Which one? Let's go up. This one right here?
Positive, I mean.
Which,
Yes.
this one? So looking at this nitrogen has, to complete our formal charge calculation, our group number is 5. We have a total of 3 bonds and 2 lone pair electrons, and that gives us a formal charge of 0.
I'm talking about the entire atom.
Oh,
I see 2 positive and
the
1 negative.
entire atom? Or you mean the entire molecule?
Correct.
This entire molecule, yes, does have a positive charge net. Yeah, our overall charge, yes, is positive.
Do you need to show it too?
Technically, you can put the entire structure in brackets and show the positive charge, but for most organic molecules, the way that we compromise in that regard is we show our entire structure, we show the formal charges on each atom, and the reader can imply the total charge of the molecule. But That's a very good question to note. Okay, continuing on, what we're now going to talk about is molecular polarity. So molecular polarity fundamentally is the net dipole or net polarity of our molecule. And there are a few main ways to go about it. I personally like the vector addition method. So we can treat our bond dipoles, which we discussed earlier on in lecture, right? We discussed earlier on in this chapter. We can treat bond dipoles as vectors centered along the bond between two atoms. And a vector has a magnitude and a direction, right? So if we're looking at HCl, right? There's a dipole pointing towards our more electronegative atom, which in this case is what? What's more electronegative? Chlorine, yep. So we draw an arrow going from hydrogen to chlorine directed along the bond, right? So it's a vector. It has magnitude, how large we draw the arrow, and direction. Where is it pointing towards? Chlorine, yep. And what this is showing is the fact that our chlorine has a buildup of electron density and has a partial negative charge. Now, the way to relate these bond dipoles to molecular dipole involves, first and foremost, writing out a valid Lewis structure. So first and foremost, we need a valid Lewis structure, and we need the right geometry. So we need all of our bonds lined up in the right orientation. Next, what we're going to do is we're going to draw the bond polarity as arrows, and we're going to utilize what's known as vector analysis. If you see a net dipole, the molecule is polar. So, have any of you taken physics previously? When you talk about vector addition, you must have learned the head to tail method. Okay, so the way it works is you draw your first dipole vector. You draw your first dipole arrow. Okay? Now, suppose that we have another bond dipole in our molecule. So what we do is we draw the second bond dipole vector, and we're going to start drawing it from the head of the first. So here's our second vector. So we have 1, 2. Okay? Now, the fastest way to add up these two dipoles is to just draw an arrow, and our net dipole is just an arrow from the start of dipole 1 to the end of dipole 2. So this is our net. And this is a fast way to draw vectors. We go from the head of dipole 1 to the tail of dipole 2. Does that make sense? Okay, so let's showcase this with a real example. So CH2Cl2, or methylene chloride, your typical polar solvent. So I'm going to draw a Lewis structure really quickly. Okay, so this is the complete Lewis structure. Lone pairs for completeness, just to be 100%. Now, what are our polar bonds? What bonds have a difference in electronegativity? Yep, the carbon-chlorine bonds, exactly right. So let me switch. Okay, perfect. And what's more electronegative, carbon or chlorine? Chlorine. So I'm going to draw a dipole arrow along this carbon-chlorine bond pointing towards chlorine. Okay? Now, we've established that these bonds are polar. What is the geometry of this molecule? Is there any reason why I drew my atoms in this specific arrangement? What's the geometry around carbon if we have 4 bonded atoms? Tetrahedral, right? This is tetrahedral. And this informs the relative arrangement of our bonds, right? That's why it almost looks like a tripod, right? Now, if I wanted to use the head to tail method, I'd pick one of these vectors and assign it as vector 1, and the other is vector 2. It does not matter which one you pick. Okay, so let's suppose vector 1. What direction is it pointing? Down and to the left, right? Okay, so I'm going to draw out vector 1 like so. Next thing I'm going to do, I'm going to draw out vector 2. What direction is vector 2 pointing? Down and to the right. Okay. Now, if I wanted to draw my net dipole, whoops, didn't change the pen color. Okay, one moment. Okay, so if I wanted to draw my net dipole, I draw it from the head of 1 to the tail of 2. So this is my net dipole. So if I'm drawing my molecular dipole, it's almost pointing directly down in between my 2 chlorines. So this is a way of estimating our net molecular dipole in a more mathematical way. Now, why are these 2 dipoles the same length? Are they the same bond? Yeah, if they were different bonds, would I draw these arrows with different lengths? Yes. Okay. So this is the mathematical method. I like it because it's much more clear cut into where I draw my net dipole. So is this molecule polar? Does it have a net dipole? Yes, ergo it's polar. And the majority of our electron density in this molecule is on the side with the chlorines, which makes sense. They're the more electronegative atoms. Okay, let's keep going. Now, there's an interesting rule that comes about from this idea. And you can work this out for yourself, but this is a rule that I've developed to help explain polarity. So dipoles can cancel only if the polar bonds are symmetrically arranged and if they have the same electronegativity. So what this means is, and this is something that you should really pay attention to, symmetrical arrangements of polar bonds with the same electronegativity lead to nonpolar molecules. So anytime you have symmetry among your polar bonds, you will end up with a nonpolar molecule. So the classic example is carbon dioxide, right? If we look at our bond dipoles, the carbon-oxygen bond, sure, it's polarized, sure, it's a polar bond, but are these 2 bond dipoles in opposite directions? Yeah. So if you use your head-to-tail method, they'd cancel out. You'd draw something that looks like this, and you'd end up right back where you started. So CO2 is nonpolar. Now, as a shortcut heuristic, if you just need a fast, is this molecule polar or not? There are 2 rules to follow here. So a molecule is nonpolar. A molecule is not polar if these conditions are met. First and foremost, if all atoms bonded to the central atom are identical. That's the first condition. Or the difference in electronegativity between atoms bonded to the central atom and the central atom is 0.4. This mainly comes up when you talk about CH bonds. They're nonpolar, despite the fact they have a very small but non-negligible difference in electronegativity, right? Now, if all atoms bonded to the central atom are identical and the central atom has no lone pairs or a symmetrical geometry. Again, we're looking for symmetry here. These are your linear, trigonal planar, tetrahedral, and square planar. And I'd like you to try at home drawing out those arrangements and seeing why those structures are symmetrical. Okay, we will also see other types of symmetrical molecules later in this course. So anytime you have symmetry among your polar portions of your molecule, you can end up with a nonpolar molecule. Looking at CO2, is that a symmetrical molecule containing polar bonds? Does everyone notice the symmetry? If I put a mirror down the middle, if I put a dividing line, do both sides look identical? Do both sides look identical? Yes, that's the idea of symmetry. Identical portions of your molecule about a certain axis. Now, if these 2 conditions are not met, your molecule is polar, and you're good to go. Does that make sense to everyone? So what two things are you looking out for here? What two things do we need to pay attention to? First, what atoms are bonded to our central atom? And then second, what is the geometry of our central atom? Okay? In general, lone pairs are a big red flag that you're dealing with a polar molecule, potentially. So, let's take a moment and let's just reflect on this. So is water, which looks a little bit like this, is it polar or non-polar? So let's try to use the heuristic and let's draw out our bond dipole. So first and foremost, is the oxygen-hydrogen bond polar? Yes, it's a polar bond, right? So let's draw out that bond dipole. Okay. So if we were to add up our bond dipoles, we'd get a net dipole that's pointing up towards oxygen. Wonderful. Now, considering that this oxygen-hydrogen bond is in fact polar, does this oxygen have a lone pair? Does this central oxygen have a lone pair? Yes. So as a result of that, this geometry is not symmetrical. So as a result, we can say that it's polar. I would encourage you to get used to drawing the bond dipoles, but if you want just a quick assessment, this heuristic has some use. So we still have some time, so what I'd want everyone to do is to focus on drawing out some Lewis structures for the following molecules. Try to draw out a 3D molecular drawing with the bond angles, and then I'd like you to draw an arrow to showcase the net molecular dipole. Where are our bond dipoles pointing? Just like we did for water. Yep, that's good. Yep, that's good. Yep, that's good. Yes, I'll be right there. Yep. Yep. We won't put on top because you want to minimize the lone pairs repel the bond substantially, and you want to minimize lone pair interactions with the bond. Yeah. Any questions? Looks good. Any questions? Just two. Almost two. Yep, it's an oxygen equivalent. Yep. Any questions? So let's take a moment. So let's take a look at this structure. I'll show you both the Lewis and the bond line structure while we're here. So there's our bond line structure, and our Lewis structure looks something like this. Of course, the oxygen has two lone pairs to complete its octet. Now, in terms of geometry, if we wanted to draw the proper geometry for this oxygen atom, what is the geometry? Whoops, wrong color. What is the geometry surrounding this oxygen atom? What is the geometry surrounding this oxygen atom? It has two bonds and two lone pairs. Bent. So this oxygen atom is bent. Okay, so we're dealing with an asymmetrical geometry. So we have the oxygen with its two lone pairs. The carbons are tetrahedral. And do we have any polar bonds in this molecule? Do we have any polar bonds? Yep, the carbon-oxygen bond's polar, right? And our dipole points towards the more electronegative oxygen. So if we look at our two dipoles, are they pointing in the same or opposite directions? Same. Well, opposite with respect to the x-axis, same with respect to the y-axis. So then we average our two arrows together and we get a dipole that's pointing up towards oxygen. So is this molecule polar? Yes. We can do the same thing for thiomethane. So the bond line structure for thiomethane looks pretty boring. Remember, thiol is a sulfur equivalent of an alcohol. It looks exactly like an alcohol, except you have a sulfur instead of an oxygen. If we wanted to have a Lewis structure, again, we draw out our methyl bonded to our thiol functionality. Perfect. Now, in terms of geometry, is this thiol also bent? Yeah. So let's draw that out now. So we have a tetrahedral carbon, and we have a bent thiol. So then, if we think about our polar bonds here, do we have any polar bonds in this molecule? Yep. Which one? Carbon, sulfur, yep. And it's pointing towards sulfur. And what else? Sulfur, hydrogen. Perfect. So in the end, if we add up our dipoles, do they cancel or do they add together? Yeah, they add together. And we end up with a net dipole pointing towards sulfur. So these two molecules are polar. Does that make sense? Does this look like review from 101? Yes. The overall direction of all of your bond dipoles. Yep. So we still have a little bit of time, so let's keep going. Let's take a moment and let's look at these next two examples, and I'd like you to tell me whether or not any of these two molecules are polar. Not the bonds, the molecules. Any questions? Any questions? Okay. Any questions? No. Okay. Any questions so far?
No.
Okay. Oh, did I draw any negative formal charges?
Well, I was thinking about this one because it only had the 3 bonds. Right?
But what else is attached to that carbon?
Well, we have the 3 hydrogen here, and there's one right here.
Yeah.
But this only has 3.
3 bonds to carbon and then 1 to hydrogen, right?
Oh,
Yeah. Oh no, it's okay. Yep, let's do it. It's good so far. So let's take a moment to talk about these examples and let's assess. So drawing out the Lewis structure, first I'll show you the bond line structure for this. Okay. Next I'll show you the Lewis structure. Okay, now, obviously the geometry of carbon is going to be what? Tetrahedral. But do we have any polar bonds, any significantly polar bonds in this molecule? Nope. Is the carbon-hydrogen bond considered polarized for the purposes, is the difference in electronegativity large enough? Nope. So then we just write no molecular dipole. CCl4 is an interesting example, and it showcases a phenomenon that you'll commonly see when you deal with polar bonds arranged symmetrically. So CCl4 or carbon tetrachloride looks a little bit like this. Now, the one real problem that I often see students or even undergraduates who are in research labs is they try to use carbon tetrachloride as if it's a polar extracting salt. When in fact, as we'll see, what's the geometry around carbon? Tetrahedral. Okay? So then we have a tetrahedral carbon with 4 chlorines attached. Now, when we talked about symmetry and symmetrical arrangements, is the tetrahedral geometry a symmetrical geometry? Yes. Are all of the atoms bonded to carbon the same? Yes. So if we draw out our dipoles, and you can prove this to yourself using geometry, though the proof using geometry is a little bit tricky. So if we drew out each of our bond dipoles, we'd see that even though we have arrangement of polar bonds, our overall molecular polarity is 0. All of these dipoles cancel out. And it has to do with the fact that the polar bonds are arranged symmetrically. Does that make sense to everyone? Okay. Now, one thing that you do need to really appreciate is that the molecular dipole is the sum of all dipoles accounting for bond direction and bond dipole strength. Adding more polar bonds does not necessarily mean you have a more polar molecule. So, to showcase this, I'd like you to take a moment and let's just look, just as our last thing to do in class today, to compare the difference between CHCl3 and CCl3F. So the only difference is that we've replaced a hydrogen with a fluorine. And you think, oh, we're adding polar bonds. That must help, right? But if we compare these two molecules, let's draw these out for comparison. You'll see something a little bit odd about our bond dipoles. We'll see something that's a little bit interesting about our bond dipoles. So when we replace this hydrogen with a fluorine, zoom in on this. So when we replace the hydrogen with a fluorine, so all of these chlorines have a dipole that's pointing down overall, right? They're on the bottom half of our molecule, right? So that's all fine and dandy. When we replace the hydrogen with a fluorine, what direction does this carbon-fluorine dipole point? Is it pointing up or down? What's more electronegative? Fluorine. So is it pointing up or down? Up. Now, this creates a whole host of issues because now we have 2 dipoles pointing in opposite directions. So we end up with a less polar molecule. So really just appreciate the fact that adding more polar bonds does not necessarily mean you have a more polar molecule. And with that, we'll be done for today. So in your textbook, this is the end of, I believe, about halfway through chapter 2. We're going to finish up and talk about intermolecular forces next class period, and then move on to resonance and acids and bases.